Okay, we left off, we were working a problem or two, work another problem, another Ohm's Law problem, and then we'll take a look at some other formulas. Another one that crops up frequently. Let's see, we want to know another example here. We want to know the watts again, and that are being dissipated when a current of 7.0 milliamps of current flows through a 1.25 K resistor. Okay. Now, we have current and we have a resistor. Well, current we can do, but we need a resistor here of some sort. And so let's see what we can do to get that. We might want to use, let's see, we don't have voltage. Yeah. So let's do, they're not giving us voltage and we need power. We don't have any resistors down here, so none of these are going to work. So this is the one we're going to use, but we need to substitute something in for this E over here that has resistor and current, and that's our other sister equation right over here. So we're going to use I times R for that E. So our power then is equal to I times R, that's in for that P, times our current again. So this is going to give us that our power is equal to I times I is I squared. So I squared R. This formula is pretty handy. This probably gets used more than the others that get substituted. This one pops up quite a bit, it seems like. Anyway, we can use it to calculate that. So we have, it's just a straight multiplication problem, and we have 7.0 times 10 to the minus 3 power. That's milliamps. Okay, and this is going to be multiplied times our resistor of 1.25 times 10, and since this is kilo, that's going to be to the positive 3. So we can do that right on our calculator. So let's do 7.0, don't really need the 0, but we'll do it for form, times 10 to the negative 3. Just a word of caution about that. Use the negative. Sometimes it's a plus minus. On this one, it's just a minus. Try not to use the subtraction when you're making a negative number. And this is multiplied by 1.25. 1.25 times 10 to the positive 3. So our exponent should probably cancel out. Let's see what we get here. And we get 8.75 watts. And I'm not sure that that is actually the correct answer. No, it is not. We should have gotten milliwatts. So I screwed up. Well, let's try it again. Let's try it without the powers of 10 here. We you probably already guessed what it was that I screwed up. It is 7.0 times 10 to the negative third power. However, this whole thing here, I'll put it in parentheses to emphasize the fact this is I squared R. So let's make this squared times our 1.2. Virtual calculators don't work well. 1.25 times 10 to the third power. And yes, we get 0. It's supposed to be a squiggle. 0.06125. Let's make a scientific number out of that. 1, 2, 3. So we have 61.25 milliamps of current. All right, great. Now, let's take a look at something else here. And this all, by the way, is all in Chapter 4 of the ARRL guide, particularly on page 4-2. They have those cute little circles I had up at the top of the page for power and whatever. So the next thing we need to do is power and voltage ratios using dB. And the power ratio, and it is a ratio, is equal to, and how it's listed in the book is log -1, which means inverse of whatever the decibel is over 10. And the voltage ratio is pretty much the same animal. It's also the inverse log of the dB, but it is over 20. Now, this notation, I'm not sure what calculator these guys were using at the ARRL when they put this together. I have scientific calculators from all the major manufacturers, and none of them list the inverse log key as this. The inverse log key up here, if you actually look at the log key, it's 10 raised to some power. Okay? So that's the same animal as this. So instead of typing in log or anything, just raise 10 to whatever this ratio is, and that will give you what you're looking for. Okay. So let's see here. Yeah, I'm just reading at the bottom of the book. Sorry to be so long here. Very useful value to remember is that any time you double the power or cut it in half, there is a 3 dB change. And this is actually one of the questions on the test. They ask you if you double the power, what does the dB, and there's no calculation. But there is a calculation. We can do dB being equal to 10 times the log of base 10 of 2 over 1. And so we can put that in the calculator with the log key. This is base 10. If it doesn't say what it is, it's base 10. But actually, we want to get 10 times that value. Damn it. Okay. And since this is a ratio, let's put our fraction there. Actually, is just going to be 2 because it's 2 over 1, which is 2. But let's put it in like it is in the book and close that off. And this gives us a value of just a gnat's whisker over 3 dB. So there's verification then of the increase or decrease. So it's about 3 dB. That's a good value to remember. Okay, so there's 2 more formulas there that you can pack away the power ratio. Power ratio is dB over 10. Voltage ratio is dB over 20. And use this key. Unless you have an inverse log key, then by all means use it. But this is the key that they're talking about. All right. More stuff coming up.